get started. I'd like to welcome Milena Capiglioni to visit the NIH to give a talk and interview. Currently, just to start out, she did her bachelor's in physics and also her master's in physical science at the Balcero Institute at the University of Cuyo in Argentina. And she was a PhD student at the Institute for Diagnostic and Interventional Neuroradiology at the University of Bern, and that's where she's doing a postdoc as well. And her work is on something that I've been thinking about for many years, and some of us have also been working on trying to do direct neural current imaging using, in this case, sort of a spin lacking approach. And we'll be talking about that for the most part. Great, welcome.
Thank you. Hello, everyone. I will be talking about the spin lock fMRI, which is now not so new anymore, from our technique for direct detection of oscillatory magnetic field that we wish are coming from neuronal activity. And I'll try to address the question of how can we move this technique from phantom to humans. Doesn't work anymore. So also doesn't work. Yeah. So you already briefly introduced me. I studied physics in Argentina, where I did my bachelor and master's, and there I work a bit on diffusion, MR, developing analytical models, but also, there you go, measuring in a 9.4 Tesla Bruker scanner to see if we could track microstructural diffusion and get diffusion sizes. Then I moved to Switzerland. Nope, doesn't work again. There you go. Where I did my PhD at the Support Center for Advanced Neuroimaging. That's where I'm still at. That's within the neuroradiology department of the University Hospital in Bern. And there we have 7 whole body scanners, but only the Prisma 3T and the Terra 70 are dedicated purely to research. So that's where I'm mostly at. And my focus is in field of fMRI, but I'm also part of the projects of morphology analysis and MRS quantification algorithms as part of PhDs and masters in our group. So going directly into spin lock fMRI and why we want to develop yet another functional technique. So we know that with both we are detecting the hemodynamic response to neuronal activation, and this will give us a direct signal for each voxel that we are imaging. So we are directly encoding spatial information there, but the functional information is encoded indirectly. And then within the non-MR related methods, EEG and MEG will directly encode electromagnetic fields, but they will do it on the scalp. And then we need to solve the inverse reconstruction problem to see where the source of the activity is. So here we have direct functional encoding, but it's spatial encoding is done indirectly. So this gap of not being able to map both things at the same time is already super interesting for cognitive neuroscience. Within the scan group, we are interested in how this affects epilepsy. So epilepsy will generate recurrent spontaneous seizures. These are like sudden bursts of very strong and synchronous neuronal activity. And it's a very common disease, but also 1/3 of the patients will have refractory epilepsy. So they don't respond to a seizure medication, and then resective surgery is the preferred treatment. So it's quite crucial that we can identify which area of the brain to take out so that they gain seizure freedom. The good thing about this, so this area post-surgical is called the seizure onset zone. And the good thing about it is that we can identify it because it will present abnormal neuronal activity even outside the ictal period. So before and after the seizure, we also see neuroelectric discharges. And what we normally do in our clinic is first we try to manage with the non-invasive methods. So we will do scalp EEG and anatomical MR. And if the finding of the suspected seizure onset zone in EEG matches any type of anatomical abnormality, that might be enough for surgical planning. But mostly that doesn't happen because many patients are MR negative, so they don't have any abnormality. So then we have to go into intracranial EEG, which means we put the electrodes inside the brain And this will give us better spatial resolution. The issue is, of course, it's invasive, but also we still need very good prior information on where to put the electrodes. So even by itself, it's not sufficient. We also use both in our standard practice, but we do it mostly once we already determine this presurgical, we did the presurgical planning of the seizure onset zone. We want to see how much this overlaps with the cognitive networks to estimate post-surgical outcome. There have been some studies analyzing the clinical utility of both to detect the seizure onset zone. The issue is that first, we don't know how the hemodynamic response is to interictal epileptiform discharges. And there are two main issues with both to directly detect the seizure onset zone. The first is if there are changes in vasculature in advanced epilepsy that might change cerebral blood volume flow and therefore change the wall contrast. And also the brain has its own mechanisms to try to stop the spread of seizures. So we will have interneurons that will actually lower the initial neuronal activity before this spread, or at least that's one of the suspected reasons. Therefore, both many times shows like negative. We have a negative wall effect, and this does not necessarily correlate with the seizure onset zone. The most promising method so far would be simultaneous EEG fMRI. There have been some studies showing that if you use the prior from EEG to see when to analyze the hemodynamic response, this will correlate with the seizure onset zone. The issue for us is that this is not the standard in clinical practice, and we want to do this in an emergency setting, so we cannot have simultaneous EEG fMRI. And in terms of biomarkers, in the last decades, there have been many studies showing that high-frequency oscillations are good markers for the seizure onset zone. This is anything that is above 80 Hertz. So what we ask is if we can somehow with MR target a specific frequency of neuronal activity. And that's when a spin-lock fMRI comes in. This was initially proposed by Witzel in 2008. He called it stimulus-induced rotary saturation or the Sears effect. And the rationale behind this technique is that if we have an oscillatory neuronal current, it will induce an oscillatory magnetic field in the surrounding tissue. We know from EEG and MEG that this will have a frequency in any range from 0 to 500 Hertz if we consider physiological and pathological activity. And what we want to do is to detect this pulse with MR. So we have an oscillatory magnetic field, but the best thing to do is actually to use that pulse as an excitation pulse, which means that we want to put our magnetic system into resonance with that oscillating field. The issue is in a 3 Tesla scanner, for example, we are way off resonance, like alarm or frequency out of resonance, let's say. So we want to lower the effective resonance frequency of our magnetic system. And we know that applying any excitation pulse, what we do is we apply a pulse in resonance, and this will generate a rotation of the magnetization, and the speed of that rotation is given by the amplitude of the pulse. So what Witzel proposed was to use a spin lock preparation. A spin lock preparation in the most basic form consists of these 3 pulses, and during the long pulse, by controlling the amplitude of this long pulse, we can control the oscillation frequency of the magnetization, so we can match the frequency of the field we want to detect. If we take a look at the dynamic during this preparation, so we tilt the magnetization down to the transversal plane. Please stop me if anything isn't clear. Then we apply the long spin lock impulse, and if we are in resonance, the oscillating magnetic field will tilt our magnetization away from the from the spin locking axis. And when we come back to the longitudinal plane, we have a contrast, and that is the Sears contrast that we want to detect. Now, even from this basic theory, we do see some advantages and disadvantages. So the first one is we are directly detecting for each voxel of our image the amount of oscillatory magnetic field that we have with this resonance effect. So this is directly addressing the gap that we have in encoding spatial and functional information directly. We can target a specific frequency. Actually, we can only target a specific frequency, which means that if we have a marker, for example, for the seizure onset zone, we can go to that specific frequency, but also in cognitive neuroscience, we can try to target a specific wavelengths or the alpha activity and so on. And in the bad side, we have that first, this oscillating field can only be in the longitudinal direction. which is a strong limitation, because if not, again, we are one alarm more of frequency away from resonance. And this field needs to appear during the spin lock impulse so that we can generate this effect. So that's also a strong limitation. But with this in mind, then a basic series sequence will always be like this. We have a spin lock preparation that will encode the information of this oscillatory magnetic field, and then we read out the image in any way. So the first thing I did was to implement this in mainly our research scanners, and based on a previous version that we had in our center. And what we have is the spin lock preparation followed by successive EPI readouts. And I optimized this as much as I could in terms of timing, but also adding water excitation pulses and adiabatic preparations for the spin lock effect. And once I implemented this, I wanted to test the effect. So we built this electrical phantom, which is a loop coil connected to a function generator that is outside the scanner. So there is like that cable is like 5 meters long to go into the scanner. And by controlling whatever comes out of the function generator, we can control the amplitude, frequency, and phase of the oscillatory magnetic field inside the magnet. Yeah, and we also added some high-pass filter, low-pass filter, so that we don't have the RF going back to our generator. So what is the most simple proof of principle experiment would be to put a perfect oscillatory magnetic field into the loop. So that's a sinusoidal wave. We can trigger the signal so that we don't have any phase. And for example, here we did it with 90 hertz. And if then we generate the spin lock image as a function of the amplitude of the spin lock. So targeting every different frequencies in each measurement. We see that if we stand in a row outside the loop, we have a constant signal, but if we stand now inside the loop, we have this huge drop of signal because the amplitude here was huge. So if we subtract these two images at the resonance condition, we can reconstruct the source of the activity. So indeed, the effect is frequency and spatially selective. The source can be localized, but we already see a big problem, which is that we have very strong artifacts. And because what we are trying to detect is this very small oscillatory magnetic field as an excitation pulse. If the amplitude of this pulse is very small, so the excitation angle will be very small, and therefore any artifact will already be stronger than the effect we want to detect. The good news is that the spin lock impulses are used for many other fields. So we already know, for example, from the field of T1 raw relaxation that you almost never apply just a basic spin lock preparation, but you actually try to compensate for all these field imperfections. So, for example, if we do a basic spin lock preparation, we don't compensate for anything. If we then alternate the phase of the spin lock impulse in the second half, then this will already compensate for V1 imperfections in the deep down pulse. And if then we add a 180 degree, we then compensate for V0. If we implement this in the sequence and we measure our phantom, already the image quality is much better. We are still putting metal inside the scanner, so we still always get very strong artifacts. But this we already knew from T1 raw. The interesting part was to see how this would affect the Sears effect. So we simulated this and we evaluated the dynamic with each of these preparations. And what came out of it is, so the dynamic will get more and more complex as when we apply more pulses. But what was interesting is that if then we analyze what happens as a function of the initial phase of the target field, so what is the phase of the oscillatory magnetic field when we apply this spin lock preparation, in the method proposed by Witzel, in the basic spin lock preparation, we don't have any dependence with this phase. So if we measure as a function of the phase and the time of the spin lock, the contrast is bigger for the longer the spin lock impulse lasts, but also we don't have a dependence with the phase. But as soon as we try to compensate for any type of field imperfections, then we start having dependence with the phase. And the thing is, we will always acquire a time series. So we will have the patient or the volunteer in the scanner, we will apply this spin lock impulse during a long time, which means that in our time series, depending on the initial phase of the field that we catch, we will have a different contrast. And for me, this is good news because it means that if the contrast depends on the phase, then what we need to highlight is signal variance and not changing the mean, which means that it allows us to differentiate it, for example, from the Volt effect or other effects that have very slow variations. So then what we did is to test this not with one simple sinusoidal, but still very unrealistic, two sinusoidals with varying amplitudes, adding them up and then targeting each of the frequencies separately. And the point was just to show that if we target signal variance, then we can reconstruct the components of each wave as a function of time. And we can not only do it with the measurements, but also the simulations respond quite well to what we are measuring in the end. So all of this is to say that this principle works very well in a phantom. It's very easily reproducible, and yeah, we can try as many complex composite signals as we want. But the thing is, how do we move this now from phantom to humans? Since this was proposed, there have been like 16 studies in phantom, but only 3 in humans and 2 in animals. So you can see already that it's quite difficult to move these to humans. And the most important studies, I would say, first, Frongeral show with the phantom that we can detect fields down to 0.06 nanoteslas, which means that in theory, we would be able to detect also neuroelectric oscillations, which can be in the range from 0.1 nanoteslas if we are lucky. Then Chai et al., who work here also, so he combined this technique with TACS, which is great because in TACS you can try to entrain neuronal activity also at a specific frequency. But sadly, what he could see in the end was the TACS derived fields, so the fields directly that come directly from the electrodes and not really neuronally evoked responses. So he could not see neuronal activation there. And last, from it also the same one from the first paper, he directly targeted in healthy volunteers alpha activity. So he had like this eyes open, eyes closed protocol where, and he measured with the spin lock targeting that frequency, and at the group level, he could observe a significant response, but then with reduced subgroups, the sensitivity got smaller. So we are at the limit of the sensitivity of this method when we try to look at healthy physiological responses. So I will quickly go through 3 studies that we did to try and check ourselves if we can move it to humans. In the first one, we wanted to also validate it with healthy volunteers, and we wanted to have neuronal activation at a specific frequency, but also to have some type of ground truth measure. And then the only other method that will be targeting oscillatory magnetic fields is MEG, but we don't have an MEG in Bern, so I moved to Trento for a few months to the Center for Mind and Brain Sciences. It's the group of Jorge Kovacic, and they have an MEG and let me use it. So we here use a very simple stimulation paradigm with a lock design with a flashing checkerboard, and we measure with the most optimal spin lock fMRI version so far, and MEG, and also Volt. And the protocol was with, so we measured 13 healthy volunteers, and so the stimulation was a flashing checkerboard at 8 Hertz that showed only 1 quadrant of the image, and then we alternated with resting periods of 8 seconds, and after half of the experiment, we changed the side of stimulation to see if we could also localize the activity. We had a reading clue to try to get rid of that artifact, and we saw from MEG that this will clearly evoke responses at 16 Hertz, so that's the frequency that we target with the spin lock preparation. So we implemented this the spin logging sequence that is the last one that was proposed, which is called balance, right? So we avoid the TFAP pulse, but the thing is, this is supposed to be the latest implementation of this sequence. And we measure at 16 Hertz to try and target this activity, but also at 36 Hertz as a control measure. And in terms of post-processing, the thing is we can go back to the phantom, and if everything were super ideal, we would have an oscillatory magnetic field in the brain appearing every 8 seconds with 16 Hertz. So we can put that exactly in the phantom, and if we measure with this same sequence, we see the signal that we are expecting, which is higher variance during the stimulation period. Post-processing then is normally to regress the signal in a ROID in the brain would be to reduce the bolt effect in some areas. In the phantom, that's not a problem, but still, then applying high-pass filtering to reduce any physiological confound. And then if we rectify the signal, we have a periodic signal at the stimulation frequency. So if we do a Fourier transform, we have a peak at the frequency we want to detect. And that is our contrast. So every time I say we are looking at variance, we are looking at the Fourier transform of the signal at the stimulation frequency. Yeah.
So,
Then, yeah,
what are the other frequencies? Are they like?
here they are harmonics.
Yeah.
Because the effect was very strong. But we will see in a human that the strongest frequency in the end is the breathing and not the MCA.
Sorry, just to go back to that, I mean, you can see the harmonics kind of fading logarithmically, as you go out. What are the 0.6 in between 0.6 and 0.7 frequency? Are they harmonics of
Yeah,
breathing?
they are also harmonics.
Okay.
So if we simulate the signal, then they will disappear. The thing is, here we are also doing the regression and filtering. So by the filtering, when we do the cutoff, this cutoff is not perfect. This was a very simple high pass filtering. So I'm also adding some.
Yeah.
But then if we look at what happens with the subjects that we analyze, first with MEG, we could see effect in almost all of them, but already we see that this doesn't give us much about the localization of the activity. So it will have a huge blob of activity in the visual cortex, which we knew already. And then both works perfectly fine. We could see activity in all of them and lateralize the effect. So when we stimulate the left side, we see the left side. When we stimulate the right side, we see the right. Now with the spin locking map, if we highlight variance with all this post-processing, we just see noise. So directly from looking at the maps, we cannot identify not even the visual cortex. What we did then was to do what Tron did. So we grab the prior from both and see what happened in that area compared with the rest of the brain. If we do that, in some cases, we see that there is a very small peak at the NCI frequency, which is not an harmonic of any other nuisance, let's say, because we control the experiment, but still this is much smaller than, for example, the breathing artifacts. So even if we apply high-pass filter and motion correction and everything, this is still encoded into the spectra more than the NCI effect.
Did you try varying the stimulation frequency?
You mean the flickering or the time of the stimulation?
Well, both, but the flickering, I was thinking, like just to see if there's some sort of frequency that might be pushed away from like maybe the harmonics of breathing or something like that, that, you know, if you vary it a little bit, it might separate itself better. possibly.
Yeah. The thing is, this frequency is not the flickering frequency.
Oh, it's
This is
double.
the stimulation frequency, because the flickering frequency will just generate higher standard deviation, but that won't have any frequency.
Okay,
So we have the frequency of a stimulation. That's the oscillatory magnetic field that we want to detect. Then we target that oscillatory magnetic field with the amplitude of the spin lock impulse that will generate higher variance. But with this metric, what we are doing is to highlight where the higher variance, when the higher variance is. So the Fourier transform is giving you the frequency of higher variance, not the variance of the,
yeah,
There's some mathematically risky thing to this, but I wonder if you're looking at sort of the breathing frequency, if it's sort of more of a global signal, that there might be a way to sort of model it and more directly believe that it.
we try that with like ICA, ICA. We couldn't really clean it that much. I think the error here was to actually try to tell the volunteers to follow the breathing clue, because in the end they ended up moving more because they were trying to like control their breathing. That's my suspicion, but I don't know. In the end, it would have been better to let them breathe at different frequencies and not have a very clear nuisance at the breathing frequency, I think. But the message for me here is the signal is so low that we cannot distinguish it from anything else. So when we do this and we analyze this against the rest of the brain, in average, MEG will detect in 77% of the cases. These were 13 volunteers, so I think that's like 10 subjects. Then involved in almost all of them, but also perfectly lateralizes the effect. But with the spin lock, we also only saw an effect in 3 of the cases. significantly. So we went back to the phantom and we measured as a function of the amplitude of the field, which is what I think is the biggest problem. And we can see how the effect diminishes if we make the field smaller and smaller and smaller. After 0.28 nanoteslas, we cannot, maybe we can see the loop, but statistically that's not significant anymore. So the sensitivity limit for this protocol, which is very short, is only 3 minutes, would be in 0.28 nanotesla. So we went back to the MEG analysis and we put all the subjects together and we estimated what is the average magnetic field of the source for all the subjects together in the visual cortex. So we still are using the volt as a prior of where to look at. And that gave us an estimate of 0.009 nanotesla. So we are more than 1 order of magnitude away from what we want to detect. The message for me is, at least with this stimulation, this is not sensitive enough to detect this type of activity. This does not directly, so the thing is, Strong detected a field with what I think is a even lower activity of the brain, which is the alpha activity. The thing is, they use first a spiral readout, so they are not encoding the volt effect into their readout, or yes, but much smaller. And also they measure like 10 minutes, something like that, or even more for each subject. So maybe with longer sequences and trying to get rid of the volt effect would work.
So how is the 0.009 calculated based on MEG? Was it like just on the surface potentials and then you projected back to where the source and how large? I mean, it's very much a function of how large the source is.
Yes,
You know,
and you have to do 1,000 assumptions to get to that
Yeah.
estimate. So it's very rough, and that's not normal to do in the MEG because they don't care actually about the
Right.
amplitude of the source.
Yeah.
So we followed some papers, and I remember the names, where they did this estimation, and you have to assume a lot on conductivity of the tissue and also orientation of the source. Yeah, it's a very rough estimate, but that's the best we could do. Yeah, also from intracranial EEG, we tried to estimate it, but we only have that in epilepsy patients, so that's also not a measure of physiological activity. Yeah. So in epilepsy patients, we are also applying this all the time in our clinic. So first I presented this at the fMRI too. We did this very small pilot study where we had 11 epilepsy patients. They have confirmed epilepsy. And we had a suspected seizure onset zone from the scalp EEG. And we had also 24 healthy volunteers. We measured our Prisma scanner, we have the EEG readouts. And here we targeted 120 hertz as high frequency oscillations. I will discuss later if that's a good choice. But the thing is, here we are not using the optimal spin lock preparation that we studied before to compensate the brain homogeneity, because this was done in 2017, and that's the ethics that we have. So we are using this B1 robust preparation, but that's not B0 robust. So that's encoding also B0 effect. And our control measurement was a spin locking off, which means it's a volt signal. So every time we have a patient, we measure with this alternating spin lock on off during that's 600, so during 10 minutes, and we are encoding again this year's effect. And what we would expect to have if we simulate this very sudden burst of interictal epileptiform discharges at 120 hertz, what we would expect is that the spin locking off remains constant, but the spin locking on has this dropping signal, so it has a higher standard deviation. So we have the two signals as a function of time. We do the same post-processing, but then we calculate a variance map. Here we don't have a frequency of a stimulation to target, so we cannot directly do a Fourier transform of anything, but we can still calculate the SPD of the two signals and penalize whatever deviation we had in the spin lock off. So in the API for slow variations, for example. And because also we don't know where to look, what we did was to analyze what's the highest signal for each of the groups that we are analyzing. So we did a cluster analysis and we determined a cluster threshold for the healthy subjects. So that's the mean of the highest threshold exceeding 5 voxels for all of the healthy volunteers. That's the health threshold. And we look at any activation in the patient group that exceeded the healthy threshold plus 1 standard deviation. This, of course, means that many healthy subjects still have activations because it's just the mean, but our idea was to see how well these activations correlate with the EEG. Then in some cases, this is how the NCI map look like. When you have an activation, you have a stronger STD. But the thing is, in this case, for example, this is directly where the chemical shift artifact is in our EPI. So all these cases were eliminated, and where there is no clear artifact in that point, then we consider that as a possible true activation. But this meant that we have to check one by one. Within this analysis, we saw activation in 8 out of the 11 subjects, so the 11 patients. And what was surprising is that there was a big correlation between this and the EEG output. So there was a very concordance in 7 out of the 8 and at the lower level in 4, which is more or less the best you can do with EEG. And we also had some false positive, which means that we had activations in the spin log, but not in EEG, and false negative we have in the EEG and not in the spin log. The point is here that, yes, this is like promising. We are seeing higher standard deviation in the patient group, but first we are using a sequence that is not optimal. So we are not sure if what we are seeing is this double resonance effect or is actually the volt signal generating higher variance in our spin log because it's susceptible to B0. So we need to improve this sequence before being able to say that this is indeed the Sears effect. And then to close, yeah.
I'm not sure if I got it. So the people are not having seizures in the scan, right?
No, these
You're
are,
looking at the baseline activity and assume that kind of at these 120 hertz.
Exactly. So yeah, I will show some results from intracranial EEG. We are targeting the 120 and as interictal epileptiform discharges. So no, within the ictal period, we never put a. Yeah.
Wouldn't there be a way to make the spin locking more broadband, like a series of very short blocks, like a short blocks? Like ultimately, it's always convolved with a sync function, right? And if you make the spin locking parts shorter, you would have some tuning width of the frequency bandwidth.
Yes, so that was proposed by Halpern, and I think that was the second spin lock paper.
Okay.
The issue with that is, for example, you can either modulate the amplitude of the spin lock, so you swept all the ranges during the spin lock. That also works in the Phantom. I tried it. The issue is that then you are like less than 1 millisecond at each frequency, and so. First, we don't know what we are targeting, and I think that's the most important point. In the alpha activity, then we would have one frequency, and we could say, okay, you move through the range from, I don't know, 8 to 12 hertz, that would work. But here, if we don't know if we have that frequency and we are such a small time during that frequency, the chances of catching that field are very, very small.
Yeah, it seems that, yeah, if you could design like an iterative sequence that somehow, you figure out which one is more sensitive and then it sort of focuses it on that frequency in some sort of iterative way. That'd
Yeah.
be interesting.
Yeah.
That would be, yeah. Without real-time fMRI, all sequence modification, so.
Yes.
Not possible.
The bandwidth right now is 20 hertz. So if you see the curve of the double resonance spectrum is around 20 hertz, so you are catching anything.
And that's given by the spin lock duration.
No, the bandwidth, no. The bandwidth is given just by the resonance effect. The spin lock duration will only give you, if you go into resonance, how much you deviate from the spin lock direction. So.
I like the face.
No. Maybe I can show it here. No.
You can talk about it later too, the morning.
No. The thing is, so in the most basic of the preparations, if you apply this spin lock impulse, what you're doing is your neuronal field is the excitation pulse. This is only locking the magnetization. So the longer that you lock your magnetization, if this field is present, then you will accumulate this tilting out of the spin lock direction. But that's the only way that you are modulating with the time. So here, the longer you measure, is the higher you have. Right? The only dependence that you have is the phase, but that is, we cannot control it. Yeah, I don't know if that answers.
So it's a complicated thing to think about. Yeah.
Yeah, but the
Thanks.
thing is,
Yeah.
the longer you measure, the higher your series count.
Makes sense, yeah.
One other quick question, still thinking about the activation study, I mean, there is a potential issue of, during rest, during, the rest of the brain during the stimulation is also, experience, has spontaneous frequencies from, 8 hertz to 100 hertz. And 32 hertz is, close enough to gamma range that you might get other sort of ongoing activity. I mean, the usefulness of that one study that you showed with BMO is that they were looking at 10 hertz, either on eyes open, eyes closed.
Yeah.
And so it's kind of like, looking at sort of a baseline activity that was changed.
Yeah.
And I'm just wondering if, that's why I was thinking of moving around the frequencies to try to get away from the ongoing brain activity frequencies possibly.
Yeah. So the thing is, the control measure should always be an spin log at another frequency, because that will encode anything that has a frequency. So that's the only way that you can ensure that the activity that you're seeing is at that frequency and that you're not encoding any type of nuisance. So in this study, we didn't do this, which is a super strong limitation. The issue is also which frequency do you choose as a control?
Yeah, right. Yeah,
It's
It's
a
tough.
alpha happening spontaneously as well. It's just-
Yeah. right.
Uh,
Yeah, it's tricky. Yeah.
Yeah. So, I think here. Yeah. And the last study I want to mention, this is still ongoing. So this is, my PhD was part of this project. It started in 2018, and the idea was to use data from all the centers in Switzerland, or the 8 with the highest, with the biggest hospital. And the idea was to recruit the 500 to 600 patients that came with a first seizure. Because one of the issues that we have in epilepsy is that, so epilepsy is the recurrence of seizures, when you have more than one seizure and it's not directly coming from a stroke or another, another thing provoking the seizure. So the issue is that if you treat epilepsy with anti-seizure medication, you need to do it as fast as you can. But when a patient comes with a first seizure, you don't know if that's epilepsy or if it's a stroke or anything else. So the idea was, okay, let's scan every patient that comes with a first seizure and try to predict if they will have a second one. For them, we use like a battery of methods. We use this also old version of the sequence, also perfusion, empiration, EEG. And the idea was to then combine all these methods to see how much they correlate and make a prediction, and then in the 2-year follow-up ask if this was indeed epilepsy or not. This hasn't happened yet because of COVID. We kind of got a crazy delay on this, and we are still acquiring the 2-year follow-up. But what we did with a few of the patients that we have, so we have 51 patients and healthy volunteers in Bern that we scanned, and we did more or less this also cluster analysis. So the sequence is the same as spin locking on and spin locking off. We measured, we calculate the variance of the map, and we again look at the clusters. And what we wanted to see here is where is the highest activation. And here we target 120 and 240. And what we saw is that if we calculate the average cluster for all the subjects, either epileptic seizure or controls, we saw that there are higher clusters in the epileptic seizure group that exceed the threshold. Whether this is an indicator of the seizure on its own, we don't know, because we don't even know if they have epilepsy. And that happens more at 240 hertz. So the thing is, again, we have like a finding in the epilepsy, but we don't know if this is, for example, just that the volt effect is stronger in these patients and this is encoded into the spin lock. We need a 2-year follow-up. And yeah, for me, the most important is we are not being able, this old sequence, to separate from any other compounds. So what we know so far of this technique is it works in a phantom. It directly targets this gap of encoding both things at the same time, but only at one frequency. But that's also good if we want to target a specific frequency. in theory, we can reach nanotesla levels, if we can do this in humans. We don't know. There have been more abstracts. I know this is a very small number, but it went up actually. So that's the highest number that we had of spin lock fMRI abstracts in this ISRM. On the bad side, we have the very low sensitivity and still the intrinsic limitation that this field needs to be in the set direction and needs to appear during the spin lock preparation. And with that, we will never, so we cannot get rid of that issue. In terms of how do we validate this, there is a general lack of ground truth. Let's say, how do we plan an experiment where we are trying to use a ground truth for something that we cannot measure otherwise? And if I would have to say, the ugly thing is that then in epilepsy, we have these promising results, but we don't know really what the signal is coming from, and the current readouts encode the Ball effect. So can we move from the phantom to humans? The answer is I don't know. And just to close, the future work is for me a bit to answer this question of what do I really want to see in epilepsy, for example. And for that, I want to get all the intracranial EEG data from these phase 2 patients, so the ones that we had to do the intracranial EEG. And I already got data from 12 patients, and here we have the periods before and after the seizure. So of course we avoid the seizure because we cannot put the patient in the scanner, and a clinician mark all the fast oscillations that they observed in the intracranial EEG. And these were the ones that were used to highlight the seizure, so to define the seizure on its own. And we can, then what I did is just, they have many fast oscillations. This is 6 minutes of readings before and after the seizures, and they already have a lot of fast oscillations. And if we plotted a function of all the subjects and the mean duration of that oscillation, we first see that the mean duration is 0.7, most of them are in the 1 second range. So we are trying to detect something that occurs during 1 second in 6. So many times, but it lasts for 1 second in 6 minutes. So it's a very, we need a very high duty cycle of the spin lock in order to detect this. So if we have a slow readout, as we do now, for example, then the chances of catching one of these effects during that time is very small. So we need faster readouts. And also the other thing is, okay, which frequency do I want to target? So whether high frequency oscillations are a good marker or not of the seizure and so on is also under discussion in the intracranial EEG community, and which frequency to target. We are not choosing 120 Hertz, but is this good for all the subjects? At least for these 12, no. We wouldn't have seen anything in these 12 subjects if we target 120. Some of them have clusters at 60 Hertz, so we could say, okay, next time you measure at 60 Hertz, but still it's very variable. So every, as mentioned, the patient number, the main frequency for that is also an ICA, and I just chose the main frequency of each fast oscillation. It's also very hard to choose a frequency to target. So it means that also this method would never be auto-sufficient by itself. So we still need a lot of information from EEG, for example, to say which frequency to target. That in terms of epilepsy, but I want more patients, not only 12. And then what I'm doing now is try to optimize the readout. So first I implemented, this is with the spin lock preparation. Oh, this is about reconstruction, but the field with the radial readout. This is a week from Siemens, but it's also still quite slow. So I'm trying to move to PulseSec to implement 3D spiral with the spin lock, which I think is for now the best option that we have. Yes, and that would be it.
Yeah, it's tricky. There's many different directions you can go with this. I mean, yeah. Right. I mean, it seems like as you learn the predominant frequency of epilepsy, or maybe if you target the frequencies that are reduced, maybe with epilepsy or something, you could like, I mean, there's space to explore. Is there any way of like, you know, building the contrasts, like accumulating it over time, if you could somehow preserve the magnetization and somehow, you know, with spin locking, it's good, but you could sort of build on that and sort of preserve that vagusation and just keep on, I don't know, it seems like that, yeah, I mean, I'm just thinking off the top of my head, trying to figure out ways of increasing the contrast. But
Yeah,
yeah, I mean, I think that the spin locking method is one of the best methods. Yeah, there are other ones that you could use in combination. Yeah, but yeah, no, this is, it's intriguing. So with epilepsy, what is the, so if you detect something, so that looks really, your last graph looked really promising. That it separated the subjects, the patients,
yes.
really well. And so that was looking like just everywhere in the brain and,
The whole brain, of course, eliminating again, the clinician went through all of them to eliminate any type of artifact from the cluster analysis. But thing here, I don't know if we are really encoding this effect, or for me, this could easily be bold, actually. Because this preparation is very susceptible to any change in B0, and because we are acquiring a time series, then if we have any type of variations in the bold signal, or yeah, in any, we would be encoding this as an artifact in the spin law. So, and we also did actually with this same old sequence visual stimulation experiment a long time ago, which is under revision now for forever. Because the issue is that using the spin locking off as a control measure is very, it's not a good control measure.
Yeah.
Go ahead. Pushing a bit on this one, if it turns out you're getting clinically relevant information on bold as an artifact, for spin locking, that's not good, but for epilepsy treatment, that actually might be good. So I'm curious, sort of pushing the other way, like, if this is something we haven't really seen cleanly or bold before, is this something that might end up directing to sort of a more widely implementable use of bold as a predictive measure here?
Yeah, that's a great question. That's why we keep doing it, to be honest, because we do see this correlation between what we are measuring and this. We also have for all these patients in the, no, not in the Swiss first, but in the previous study, we also have the bold in resting state. We did some network analysis to see if we could see where the activity was lower, but it was a bit of a mess. We didn't see anything particular. My question would be, if because this preparation is so susceptible to B0 imperfections, we are actually seeing the changes in B0 that come from neuronal activation, even if that's not this beautiful resonance effect, then it's still useful, yes, but we don't know.
Yeah, so you had said, one of the summaries was that you didn't think that spin lock was necessarily accepted enough to directly detect these neuronal responses at 3T. So I don't have a good feel for the field. So what is going to 7T do for you, if anything? Just complicates it, or?
It's a very good question. Maybe I have it because, yeah, that's very simple, but many of the latest studies in this technique were actually going to the lower field and even ultra low field, because then you don't have such a strong imperfections, and we know from the spin law that we will be encoding everything. So in that sense, it would be much better to go to ultra low field and then we get rid kind of the bold effect and also the imperfections. The issue is then, of course, SNR will be much lower, but this is the direction where it seems to be going. And in terms of the ultra high field, I have now implemented this in the 70, and I'm starting to try it. We should have there definitely a ultra short echo time readout, because the bold effect will be just too strong there. So we cannot do with an EPI at 70, that's for sure. And in terms of field imperfections, I don't think the composite preparations will have such a strong issue. The issue there is to measure with my phantom in the 7 Tesla. Because the loop coil, which is not magnetic but still disturbs a bit the field in the 70 stereo. And we bought already many types of loops, and we build them and always go, but in a machine these are just too big to measure. So I could never really test it so far.
Oh, I see.
But it's something that I want to do, yes. There are these EEG phantoms. For simultaneous EEG fMRI, they have like these agar phantoms, And what I wanted to do was to do like TACS on the phantom, and then I don't have to put the metal of the coil.
Okay,
Yeah, that would be my approach, but
So, but also at 7 Tesla, I don't even know, I mean, are there start limits for the pulses?
not really. So here we are going up to 240 hertz, and I could also do that in the 70 with no problem. So the sequence run is very ugly, but it runs with no problem.
Okay, so there's no limits of, okay, the power deposition people that's higher.
No, and also with the composite preparations where we start applying a lot of 180-degree pulses, then it gets a bit worse, but at least until 240 we can measure. And in the physiological range, so alpha waves and that, we don't have any problem.
So you do have the magnetization preparation module for each slice or for each volume? No?
Not currently. No, and here in this epilepsy study, we are doing one spin lock preparation and 6 slices, and then another and the next 6 slices. In the study in Trento, I only did 3 slices around the visual cortex, so that was only one preparation. And any other study that has been done is single slice, which is also an issue. So nobody has tried this with a 3D ultra short echo time readout, which is what would be great to have.
Yeah, I mean, it's, right, it's like, it's so enticing because there's so many things that the space is big, and you think, oh, you can just find the right location in this parameter space, and you can detect it more robustly, and yeah, it's tricky. So does this imply also that epilepsy, like the current amplitude is higher with seizures? I mean,
Yeah, the neural activity, even in this ictal epileptic only starts are much higher than normal physiological responses. Like in our average controlling both of them, it was like 10 times higher. So if we have 0.1 nanotesla, then we would almost reach the Tesla. But the thing is, this is very short. And also the issue with epilepsy is that sometimes it's focal, but in other of the cases, we just have the whole brain lit up, at least in EEG. So then.
You're mentioning ultra low field here. I think for a long time, some of the ultra low field systems, you know, you are using like SQUID for detection. I don't know if anyone's been using OPMs for detection yet, but I'm curious if those systems were like the field is so low, you get away with essentially boosting up your recording tool. Could that address the SNR for this? And I know really early on the ULF system, we just weren't talking fMRI because just there's such slow readout that there's nothing left.
Yeah.
But this is a totally different mechanism, so I'm wondering if the systems that sort of ramp down the field but ramp up detection might be able to pull this off a lot better.
Maybe, I don't know. Also in ultra low field, they did like single slice slow readouts. So yeah, this has always been combined with very bad readouts, even in low or high field, sadly, but that's a good question. Yeah. I don't know if,
questions?
no, that's-
The chat is just me asking if they can hear you.
perfect.
Thank you.